Collection of unit balls. For example, this is our P. And then we study the number of incidences between P and T. That's defined as the number of pairs QT inside our set, such that Q intersect T has volume larger than, say, 1/10 of the volume of a Q, of a unit ball. So in particular, in this example, the number of incidences is 3. Here we have one for this rectangle and one for this rectangle. And the question we want to study is, can we give an upper bound about the number of incidences? With Larry Guth, my PhD advisor, and Noam Solomon, we studied this problem using Fourier analysis, and then later we'll see an application of such kind of bound also back to Fourier analysis. So let f be sum over functions phi q. Phi q is a bump function at each unit ball q. Phi q is 1 on the unit ball q, and the support of phi q is inside 2 times q. So essentially, it's like the characteristic function of q. We make it slightly smoother. And then let G equals to sum over phi t. Then we can rewrite the number of incidences by an integral. So this means less or equal than a constant factor of, we integrate f times g. So by writing this number of incidences as an integration, we can do we can take Fourier transform. And now what's next? The next step is to study what's the Fourier transform of G. So G supports on the union of those rectangles. If we have a rectangle T, and the Fourier transform of phi t is essentially support on a dual rectangle T star. I will draw it larger. So the dual rectangle T star has length 1, that corresponds to this direction, and has width 1/r, which corresponds to this direction.
So here also you smooth the characteristic function?
Yes. And now G hat is a sum over those phi t hat. But another thing is, since phi t is like the characteristic function, the essential support of phi t hat is centered at the origin 0. And now we take the union of all those phi t hat, then it will become the union of the tubes or the rectangles passing through the origin inside roughly the unit ball. And the next thing that, as an analyst, we usually do is we decompose into high frequency and low frequency. Oops. So let's say here at some r to the minus epsilon, or something slightly smaller than 1. And we decompose our G. So G into G high frequency and G low frequency. So high frequency is the part of G hat that's outside of this blue circle. And then the observation is that if our omega is on the high frequency, then there are only finitely many, up to epsilon, finitely many directions passing through this omega. So for the G high frequency, we have a very good bound. We have a good L2 bound, and then this will give us a good estimate about the number of incidences. And what happens if we are on the G low frequency? This will imply that we can reduce our problem to a good thickening of the original problem. So it means that we can thicken everything to a larger scale. This is essentially the method that we had to study this problem. This method was inspired by Thomas Oppermann and also Wien. It has some consequences in Fourier analysis. For example, the Faulkner distance problem and also the local smoothing problem for wave equations.
Sorry, can you say what the nature of the result is?
The nature of the result, you mean the estimate?
Yeah, the bound.
Okay, the bound is actually long. So that's why I explained the method instead of the bound. So it bounds the number of instances by the number of points and the number of rectangles.
So also, after you do this thickening, then do you repeat the operation?
Yes.
There's an induction there?
Yeah, there is an induction. This means that it's good. We can, if we do an induction, it can close it. Yeah. The good thickening means the following. And today I'm going to talk about an application that's related a little bit to number theory. What time? How much time do I have?
5 minutes.
Okay, great. So if we are interested in counting the number of integer solutions, so this means all the positive integers from 0 to capital N satisfying N1 plus Ns equals to Ns plus 1 plus N2s, and then all the powers until D. Then the number of integer solutions to those equations, to this system of equations, equals to the integration of an exponential sum. Then a few years ago, by Bourgain, Demeter, and Guth in 2016, and then Trevor Woolley, they showed that this is bounded by epsilon is any positive small number times n to the s plus n to the 2s minus one can see that this is the best possible we can hope for. This is called the Vinogradov mean value theorem. And then we look at a different version of it, saying that if we look at a smaller interval on the xd coordinate, and then this is no longer equal, the conjecture says that we should have the following bound. This is conjecture by Heath-Brown.
Again, it's sharp, right?
Huh?
Sharp.
Yes, it's sharp.
If
So the Vinogradov mean value theorem is the case where beta equals to 0. And then for the three-dimensional, for d equals to 3, when beta equals to 2, it was proved by Bombieri and Ivanek. And then later, by Bourgain using decoupling, they proved for d equals to 3 and beta equals to 2. And this year with Triplin Demeter and Larry Guth, we showed for a range of beta from 0 to 3 halves, also in dimension 3. And Heath-Brown uses this estimate to give some improved fourth derivative bound and give some estimate about the Riemann zeta function. So here I'm at IIS, I want to study more about the incidence estimates between different shapes and then apply them to Fourier analysis. Thank you.